Hello LeetCoders, today I'm going to solve LeetCode problem number 1162, as far from land as possible. So in this problem we are given an n by n grid which consists of values 0 and 1. 0 represents water, 1 represents land, and we need to find a water cell such that the distance to its nearest land cell is maximized, and we need to return that distance. If not, then we are going to return a -1. So now let's just see what does this mean by maximizing the distance to the nearest cell. So let's look at this example here, which is given in our LeetCode problem itself. So this is land. 1 represents land, 0 represents water, right? Now we need to find distance to the nearest land which is maximized. So basically we need to find maximum of the distance that is maximum of all the distance between the land and the water. So this is what we will have to find, the maximum of the minimum distance. So now what's the minimum distance? Basically minimum distance is the distance between the land and the water. So we need to find the minimum of those. Now let's look at this example here. This is land, this is the water. So what's the distance? So basically distance is found using this formula, the Manhattan distance, that is just subtracting the x indices and y indices and then taking the sum. So since this is 0, okay, 1 2 0 1 2, all right, so this is at index 0 0 and this is at index 0 1, so the distance is equals to 1 between these two, right? The Manhattan distance. And also if we take these two, the water and land, the distance would also be equals to 1. So basically for this one the minimum distance is so far 1. What about if we calculate the distance between this and this? So this water and this land, the index for this is 0 1 and the index for this is 2 0, right? 2 0. So basically distance is equals to 2 plus 1, that is equals to 3. So the distance here is 3. Is 3 minimum? No, not of course. 1 is the minimum distance, right? So the minimum distance for this water, all right, for this one is equals to 1. Similarly for this one is also equals to 1. For this value will also be equals to 1 because we have only one cell difference between the water, right? And it's the same for this one. Now what about this one? How do we find the distance for this cell? So basically to find the distance for this cell, what are we going to do is we are going to take the distance of its nearest water. So what's the nearest water? Well, basically we choose the four different directions and then we find the distance of the nearest one. So basically we take the nearest one. So here in this case all of these have the value 1, right? Since all of these have the value 1, so we just take any one of those. So we take the value of the distance of these to its nearest water, so that's 1, and we add a 1 because the distance between these two is 1, right? So that's why we add a 1, so the distance becomes equals to 2. So the distance for this is equals to 2. So now what are the minimum distances, what are the distances we find. So let's just make a new grid for the distances. Since it's a water, so we are just going to assign the value 0 to it for the lands, and for water we are going to assign the value that we found. So for this one it's 1, right? And for land it's 0, for water it's a 1. Okay, and for this value we found the value 2, so we write here 2, and then it's a 1 again, it's a 0 for land, a 1 and 0. So now we found this matrix of distances. These are the minimum distances, and what is the maximum value among these? Well, this is the maximum value, right? So we pick this value as our maximum value, which is our answer. So to solve this problem, we are actually going to create a new grid that would be of O of n times n space complexity, and we are also going to find the distance to minimum distance of water from its land. We are actually going to start from a land and then perform a breadth first search, and we store the values in the grid and use those values. So basically we are going to have this distance array distance, and our time complexity will also be O of n squared times the maximum length of the queue. That could be equals to okay, that should not be greater than m. So now let's start solving our problem. So let's create our DPP. For that, let's take the length of the grid. We are given that the grid is n by n, that's a square, so we just need one value for the length. Now let's create our minimum distance array. That would be our DP. Okay, I'm just going to write the distance here, array, and it would be of length n. Also, we need to initialize each of the rows in this distance as a vector as well, right? So distance I is equals to new array again, and we are going to fill all the values with infinity because we need the minimum distance, right? Minimum distance, so that's why we are filling it with the maximum value so that we can minimize that distance. Now that we have found that, let's create our DFS function. So we are going to pass index IZ. Index IZ will be the index that consists of land. So in this example, that would be index 0, 0, and now we have to find the neighbors that are water and find the distance of the water. So we are going to create a queue because it's a DFS function, so we need a queue, or that would be an array. And we are going to push to our queue the value ij. And also we need to keep in mind one thing. We have initially defined all the values for the distance as infinity here. Now we are going to update the value for the distance if this is a land to equals to 0. All right, now since we are looking for all the directions, so I'm just going to create a directions array such that we will be looking in all of the 4 directions. Okay, and now we are iterating through all the 4 directions. we need to check if x and y are in the range. So if x is less than 0 or greater than equals to n, or y is less than 0 or y is greater than equals to n, then we are not going to do anything, so we just continue. Else what are we going to do is we are going to find the distance, new distance. Okay, all right, new distance for our xy index. So that would be equals to 1 plus the distance at index ij, right? That is what we did. So to find the distance for this one, we define the distance for the land as 0, so we add 0 to 1, because of course neighboring cell is by distance 1, so we add a 1 and that gives us the new distance. And now we are going to check if our new distance is less than the value that's present in the index xy. That is when we are going to update our value at dp as new distance, and we are going to push to our queue the value of xy. All right, so now we have created our function, DFS function. Now let's make a call to our DFS function. So the call will be made from the create if we found a land. So if we found a land, that is when we are going to make a DFS call. And then finally, all our values will be stored in our TP, right? So we need to find the maximum of that distance, the minimum distance that we stored. So to find the maximum, we need to loop over the DP once again. So okay, it's not DP, it's actually distance that I defined it as. So let me just update these values. Okay, all right, so starting from I equals to 0, I is less than, and I plus, and again for j less than 0, j j equals to 0, j less than, and j plus plus. So our result will be the maximum. All right, and then finally return our result. Let's run our code. Okay, oh no, I again used DP here, it's distance. So we should actually look out for distance that could be infinity, right? That could be the value infinity. So if it's infinity, then we are going to continue, because there could be the case where we might not well, I don't think there could be any case, but let's just see. Okay, so what did I do wrong here? All right, so what did I miss out here is the while loop. Okay, so we actually are doing a DFS solution, and for that we need a while loop, right? So let that would be here. So while, so we are going to loop over the queue so we need our indexes xj, that would be the first element in the queue. So we take the first element from the queue, the index of the first element, and that would be the index. Okay, so this value is a land, so that would be outside here. To start from the land, right? Distance of water from the land, so it should be 1. All right, so we also need to check if the distance is equals to 0 or not. If the distance is equals to 0, then the result, we are not going to change the result. If not, that is only when we are going to update the result, because 0 means that that's a land and we don't need any land, we are only comparing the water here. Now let's try to run our code, submit it. Okay, result would be actually -1. Great.